Hi folks, in this video we're going to try and summarise as much as we can of the topic of waves and try and fit it all onto one page. The content in this video is suitable for double award physics and for GCSE Physics. If there's any material that only applies to GCSE Physics, then that will be made clear by using a different colour pen. In this particular topic, there isn't any higher only tier content, so everything here could appear on either a foundation or a higher tier paper. So let's make a start by looking at what waves do and the different types of waves that we need to know about. So the first thing we need to understand is that waves transfer energy, and they do that without transferring matter. So where a wave may appear to move from left to right, the particles that make it up do not travel along with the wave. A good example of this would be a Mexican wave. You may have seen in a stadium a crowd of people creating a Mexican wave, and the wave itself moves from one side of the stadium all the way around to the other side. However, the people who are creating that wave, they do not move from one side of the stadium to the other. They do move, of course, to create a disturbance in order to create the wave itself, but they do not move along with the wave. So we're going to look now at the two different types of waves and the motion and the disturbance that would cause that type of wave. So we have two different types of waves. We have transverse waves and we have longitudinal waves. We have a definition that you need to be able to recall whenever you're asked what is a transverse wave or what is a longitudinal wave. So let's look at the transverse waves first of all. For a transverse wave, the particles in the wave will vibrate, or you may also hear the word oscillate. They vibrate perpendicular to the direction of wave travel. So while the wave itself will be travelling from left to right, the individual particles that make it up will be moving perpendicular to that, which means they'll be moving up and down. And that's an example, the Mexican wave we talked about earlier. A person will move their hands up and down, but the wave itself will travel from left to right. Now a wave like this will have crests or peaks, which is the top of these waves, and it will have troughs, which is the bottom of the wave. Longitudinal waves, however, the particles in a longitudinal wave will vibrate, but these vibrations will be parallel to the direction of wave travel. So as again the wave will be travelling from left to right, this time the particles will also be vibrating left and right, but they will not travel from the beginning to the end along with the wave. They will just travel around a mean position. A good example of a longitudinal wave would be on a slinky spring, where you push the spring forward and all the coils will bunch up together. Now that section where all the coils will bunch up together, where they're closer together, this is called a compression. And when you have an area where they're bunched together, you will also have an area where they're further apart. And that section where they're further apart is called a rarefaction. Now we need to be able to give some examples of transverse waves and longitudinal waves. So for a longitudinal wave, there are two examples really that we would be using at GCSE. And those examples are sound and ultrasound. And we'll look at ultrasound in a bit more detail shortly. For transverse waves, we have a few more examples that we can choose from. We have water waves, and then we also have a group of waves that are known as the electromagnetic spectrum. Now we'll be looking at each of these waves in more detail again in this video, but I'll list them here as well. Information about these waves can be shown on a graph, and that graph could either be displacement against distance or displacement against time. So you will need to be able to read what kind of graph it is and take information from that graph. Displacement here refers to the particle's position compared to the equilibrium or rest position. So if there was no wave travelling through the medium, that's what we're referring to as the equilibrium or the rest position. It's undisturbed, but whenever a wave passes through, then the particles will move, they will vibrate or oscillate, and the displacement then is referring how far those particles have moved from their original rest position. We actually give a name specifically to the maximum displacement from that rest position, and that name is the amplitude. So the amplitude is the maximum displacement from the equilibrium position. You might need to identify that from a graph, and on the graph that would be shown as the maximum height from zero, which means that would take us all the way up to the top of the crest, and we would label that as A. It would be also true if we were to label from the zero position to the bottom of the trough. That would also be equal to the amplitude, because the disturbance of the wave goes the same height above as it does below. In an exam, one thing to look out for is they could potentially label from the height of the wave, from the crest, all the way to the trough. And they could tell you, for example, that this value was 20 centimeters. So if you're asked what is the amplitude of the wave, they're testing you to see, do you know that it is from the rest position to the crest or the rest position to the trough? That's the maximum displacement. It's not 20 centimeters. In this case, the amplitude would be 10. If the graph we're looking at shows us how the displacement varies with the distance along the wave or the position along the wave, then we could actually find out from this graph what the wavelength of the wave is. And that would be the distance between one crest and the next. And we use the symbol lambda there to represent wavelength. Now, the definition for wavelength is actually from one point on a wave to the same point on the next consecutive wave. So another way to identify it, the wavelength, would be to look at from trough to trough. That would also give you the wavelength. And another common one that would be useful is we could consider the wavelength to be one full S shape. So from the start of the wave to the end, you'll see here we have one loop up and one loop down. That would also be one wavelength. Those are some useful ways of identifying that from a graph. Since the wavelength is just a distance, it is measured in meters. So you might need to look out for any questions where the wavelength is given to you in centimeters or millimeters even instead of meters, because you'll need to convert that. Now, if the graph that we're given is showing us how the displacement varies with time, then there are still a few bits of information we can take from that graph. What we would find in this case is that we could still work out the amplitude just as before, and the amplitude has the same definition and it's taken from the graph in the same way. But the other thing that we could work out is the time that it takes for one complete wave. So for example, if we started off at a crest of a wave and then we read from the graph how long it took for the next crest to occur, well then that would tell us the time period of the wave, and we use the symbol capital T for the time period. That is the time then for one complete wave. Since it is a measure of time, we measure it in seconds. Now, if we know what the time period is, if we know how long it takes for one complete wave, we could also figure out what's called the frequency. And the frequency is the number of waves that occur in 1 second. So the number of waves or the number of vibrations that occur in 1 second. The time period and the frequency are linked together by the equation T is equal to 1 over F. Or vice versa, we could switch those positions and say that F is equal to 1 over T. Now the time period does need to be in seconds for that equation, and the frequency then for the number of waves per second, frequency is measured in hertz, or we would just write capital H Z for short. If we know some things about the wave, if we know the wavelength and we know the frequency of the wave, we can use that information to calculate the speed of the wave. And to do that, we use the equation V is equal to F lambda. V refers to the velocity of the wave, and it is measured in meters per second. F is the frequency of the wave, and it's measured in hertz. And lambda is the wavelength of the wave, and it's measured in meters. When using this equation, just take care that you pay attention to the units that you're given in the question. A value for the velocity, which you might see coming up again and again in questions, would be the velocity of light. Now, all electromagnetic waves, which we'll meet shortly, they all travel at that same speed. And the speed of light is 300 million meters per second, which you'll also see written as 3 by 10 to the power of 8 meters per second. So that's the same number, just written in standard form. When we're dealing with numbers that are really big or really small, it's not uncommon to see a prefix written in front of it. Now, you'll be familiar with some prefixes already. For example, centimeters. So you need to make sure that you're comfortable with changing between centimeters to meters or millimeters to meters or any other variation. So some common ones that you'll come across at GCSE would be 1 centimetre, which would be written as 1 cm, and that's the same as 0.01 metres. 1 millimetre, which is 0.001 metres. So if you wanted to change from millimetres into metres, you would need to divide the number by 1,000. Less commonly, you might come across 1 micrometre, which is 1/1,000,000 of a metre. If we look at some of the bigger values, we could have a kilometre, which is 1,000 metres, or we could even have what's called a megametre. Now, while I'm talking here about millimetres and centimetres, the same conversion applies for any unit. So instead of having 1 kilometre as 1,000 metres, I could have 1 kilohertz, which would be 1,000 hertz. I could have 1 millisecond, which is 0.001 of a second. Okay, this next little section we're going to look at is how we can show waves on a diagram using wavefronts. So this bit applies to GCSE Physics only, and I'll be using purple for it. What I've drawn on here on the left hand side is a water wave that is travelling towards a wall. It's travelling towards a boundary. Now the line with the arrow is representing the direction of the wave. But I'm now going to add on a series of lines that are perpendicular to that direction that the wave is travelling in. And this line is what we call a wavefront. This is like a ripple of the wave. It's lots and lots of crests occurring here at the same time. Now when we draw these wavefronts on, they will always be perpendicular to the direction of the wave travel, and they will always be equally spaced. And that's because our wave is moving with a constant speed, and therefore it has a constant wavelength. Now we said earlier that the wavelength is the distance between one crest and the next. And since these wavefronts are representing the crests, that means the distance between each wavefront is equal to the wavelength. Once that wave hits the boundary, it's going to reflect, and it will obey the law of reflection in that the angle of incidence will equal the angle of reflection. What we're going to do here on this diagram is we're going to complete any of those wavefronts that are not fully drawn. You'll notice that the first few wavefronts we have here, these are all complete, they're all the same length, and they're all equally spaced, including this one as well. But this wavefront, part of it's missing. What should happen is if there was no boundary there, that wave would continue like this little bit in red. But that isn't what happens to this part of the wave, because the wave is now reflected, which means this little part of the wave is now going to look like that. It's reflected at that surface. The same is going to be true for the next part of the wave. So the next incomplete wavefront, which is this one here, instead of that line going straight down as it would have done if there was no boundary there, what's going to happen is that bit of the wavefront is going to be reflected. And again, following the law of reflection, that's going to look like that. Now hopefully you'll notice there that the space between those two wavefronts is approximately the same as the wavefronts that we're going in. So I can actually now continue my wavefronts when they're being reflected. So our wave is going in that direction. So when the wave is reflected, the frequency stays the same, the wavelength stays the same, the speed of the wave is the same. The only difference that we have is that there is a change in direction. Now, if we look at another case where we draw some wavefronts onto a diagram here that is showing water, a water wave that is travelling from deep water into shallow water. So this first section represents the deep water, and this bottom section here represents shallow water. So for example, in a swimming pool, the shallow part of the water could be a step in the swimming pool. So our wavefronts are drawn, again, equally spaced, perpendicular to the direction of the wave travel. Well, this time the wave isn't going to be reflected. The wave is actually going to change direction. It's going to be refracted. And it's going to go towards the normal as it goes into the shallow water. It's going to bend. So instead of continuing in a straight line, it's now going to bend and change direction. So what we would need to do then in this diagram is we're going to complete the wavefronts. And again, you'll see that these first few wavefronts are all complete, but this wavefront is incomplete, as is this one. So we're going to complete those two wavefronts to show what happens. So if the water depth was consistent, then that wavefront would be completed with the line in red here. It would just be straight. But since it's now moving into the shallow water, it's now going to slow down. And because of that change in the speed, that causes a change in the direction of the wave. The wave's going to change direction so that the part of the wavefront that is in the shallow water needs to be perpendicular to that line that shows the direction of the wave. So our line in the shallow water, the rest of that wavefront, will look like this, where this is at right angles to the direction of the wave that we have. If I do the same with the tiny little bit of the wavefront that's left in the deep section, and that part of the wavefront is now going to be perpendicular to the direction of the wave. So it will look like that. Now you might notice there that the distance between the wavefronts that we've drawn in red are a little closer together, which means we would need to continue now with that wavelength. So they need to be equally spaced as they're in the shallow part of the water. Now when the wave is being refracted here, so the word here is refracted, the frequency is constant. So the same number of waves enters the boundary as leaves the boundary. But the difference here now is that the wave slows down in the shallow water. And when it does that, in order to maintain that constant frequency, if the wave slows down, then the wavelength decreases. And we see that in the diagram by the wavefronts getting closer together. I'll just also note at this point that we have shown a change in direction whenever the water wave is travelling from the deep water into the shallow water at an angle. However, if it was to travel straight and hit that boundary head on, that means it's travelling in along the normal, the angle of incidence is 0. Well, then we would not have a change in direction, but we would still have the wave slowing down in the shallow water. So the wave fronts would get closer together in the shallow water, but the direction would not change. So now we're going to move on looking at echoes, and this is applicable to everybody in double award and GCSE Physics. So echoes are really just reflected waves. Usually when we talk about an echo, we're talking about a reflected sound wave. Waves that are emitted in pulses, and we wait then for that sound wave to reflect off a surface and for that to be detected again. And by working out how long it takes for the wave to come back, we can figure out how far away something is. So sonar could be used in ships to detect maybe other ships or detect how deep the water is. We're actually going to look at an example in just a second. And we also have radar, which is the same thing in principle, but using radio waves. And air traffic controllers, for example, might use radar, send out radio waves, and they'll wait for the reflection to come back, the echo to come back, and they can use that to figure out how far away other planes in that are. So a common example that you could be given, I'm going to stick with the sonar that we'd mentioned before, and what we have is a ship, and the ship is in the water, and it is a certain height above the seabed. So seabed here at the bottom. What happens is the ship will send out a signal, it will send out a sound wave, and that sound wave will travel, it will hit the bottom of the seabed, and then it will reflect back again. And then it's detected on the ship. And using that time, how long it takes for that echo to come back, then the depth of the water can be calculated. So the basic equation that we're using for these calculations is speed is equal to distance over time. So what we'll need to be mindful of is the fact that In a question, if you're told that a signal is sent out and then the echo is heard sometime later, then that time is actually the time it takes for it to go down, hit the bottom of the seabed, and then return to the ship. So during that time that's quoted, the distance travelled won't actually be the depth to the seabed, but rather to the seabed and back again. So we will need to factor that into any calculations that we do. And we can do that by either doubling the distance that is travelled. So instead of saying the speed is equal to the distance over time, the speed is equal to the depth multiplied by 2 over time. Or alternatively, we could half the time taken. If we find the time it takes just to get to the bottom, then we can plug that into the equation. But it's definitely something to look out for. Is over 20,000 hertz. Humans can hear between the range of 20 hertz to 20,000 hertz. That would be the normal range of human hearing. Or we can also write that as 20 hertz to 20 kilohertz. So there's the K prefix that we met earlier. So it means 1,000. So 20 kilohertz is 20,000 hertz. Now I say that's the normal range for human hearing because that range can be affected by a lot of things. For example, damage caused to the eardrum during trauma in a sporting incident or prolonged exposure to really loud sounds. You may notice if you're ever at a concert or on a runway where an airplane is taken off, workers will wear earmuffs to protect their ears from the loud noises that are there. Also, as a person gets older, that upper range of human hearing will naturally decrease. Of the fetus by measuring the diameter of the head. So when the ultrasound approaches the baby's head, part of that ultrasound wave will be reflected and detected again by the device, which is then displayed on a monitor. There is also another reflection whenever it reaches the other side of the baby's head. And by measuring the time between these echoes, we can use that information to determine the diameter of the baby's head, and that is a good indicator of the baby's development. Finally then, we will have a look at a range of waves that are known as the electromagnetic spectrum. The names of the 7 waves and to be able to recall them in order. And we'll look at what we mean by in order in just a second. We also need to know some uses and, more importantly, some of the dangers associated with these wavelengths. So the first wave we'll look at is radio waves. Hope you remember that. Spectrum. So remember my instructions: visible under X-ray glasses. And that represents radio, microwaves, infrared, visible, ultraviolet, X-ray and gamma. So in this particular order, we're starting with radio waves, which have the largest wavelength, and we move all the way down through to gamma, which has the shortest wavelength. So going from gamma through to radio, our wavelength is increasing. Or if we go from radio to gamma, then it's decreasing. So this list is showing us the waves of the electromagnetic spectrum in terms of decreasing wavelength. Now, as the wavelength is decreasing as we go down the list, that means that the frequency is increasing as we go down the list. So the wavelength gets smaller, the frequency gets higher. And that's because all the waves on this list all travel at the same speed. And that speed we met already in this video is 300 million meters per second, which is also written as 3 by 10 to the power of 8 meters per second. So for each of these waves, we need to be aware of some of the uses and, more importantly, the dangers that can be associated with each. Radio waves are used in communications and have a relatively low danger. It is believed that very large doses can cause cancer and leukemia, and some people do believe that low frequency radio waves have impacted on their health, but at the moment that is still unproven. Microwaves are also used in communications and also for cooking food. What happens is the microwaves cause the water molecules within the food to resonate, so they vibrate and heat up, and that causes the food to become cooked. The danger of that is that can cause the internal heating of body tissues. Infrared is also used for communications and in things like remote controls. Anything that gives out heat is actually giving out infrared radiation. And if that heat is too intense, well, that can cause skin burns. Visible light is used for seeing, it's used for photography. But if the light is too bright, that can damage your eyes. Ultraviolet is used by the skin to make vitamin D, and it's also used in detecting forged banknotes. If you've ever gone to a shop and they have taken a banknote and put it underneath a blue light, that will be an ultraviolet light. It will show up any images that have been printed on the note with a special ink that usually isn't visible to the naked eye, but underneath the UV light, that image becomes clear. And if a note doesn't have this, then it would be a forged note. Too much of this ultraviolet light can cause damage to your skin cells, which ultimately can lead to cancer. X-rays are useful for detecting broken bones, but again can damage cells, which leads on to cancer. Finally then, we have gamma radiation. So it has the shortest wavelength here and the largest frequency. It can be used in treating cancers and for sterilizing medical equipment. However, it can also damage cells, which leads on to cancer. So all of these waves have a few things in common, which you would need to be able to list in an exam. So hopefully now this will make it easier. When you are asked to give an example of a transverse wave, you can list any of these waves in the spectrum. All EM waves can travel in a vacuum. So that means that they do not need a medium to travel through. Sound is an example of a wave that needs a medium to travel through. It needs something to vibrate. Whereas with electromagnetic waves, they can travel through a vacuum. For example, space is a vacuum. That's why we are able to see light that has come from the sun, because visible light is an electromagnetic wave. We can feel the heat that's produced from the sun because that's an infrared wave, but we don't hear the sun burning. We don't hear the nuclear fusion that's going on in the sun. And finally, all electromagnetic waves travel at the same speed in a vacuum, which is the number we met earlier, 300 million meters per second, or 3 by 10 to the power of 8 meters per second. This is usually the number we'll use in any calculations because the speed of light in a vacuum and the speed of light in air are extremely similar. So for GCSE level, it's fine to use that same number. So that's the topic of waves and sounds in the electromagnetic spectrum, summarised as best we can, fitting it all on to that one page. The next thing to do would be to look at some worked example videos and to try some practice or past paper style questions, and that will really test your understanding of this topic. So I hope that you find some of that useful.